activity. Okay, if you keep it under 30,000 counts or under 10, depends on if it's a large field of view camera, you can probably get away with about 30,000 counts per second. But that's why I put a range here for 10,000 to 30,000 counts per second. The more counts you get, the higher the dead time, and the more distortion and problems you're going to have with your image. In Paul Christensen's book, they used to have a beautiful picture of what happens when you have too high of a count rate. They don't have that picture in there anymore. I'll have to see if I can find an earlier edition of the book, because I think it's well worth looking at to see that. But they call that temporal resolution. Temporal means time resolution. So basically, how fast can your gamma camera process the counts? If there's too many counts, then you lose resolution. So, do all of you do a photo peek before you start doing your imaging? Yes, no, maybe?
I did this morning.
Okay. Well, remember, what you want to see is something like this. Okay? You want to see a nice, sharp photo peek. Remember, we measure full width at half max to determine the energy of these things. Okay, so remember we have these little characteristics. Here's the Compton edge here, and then here's some X-ray characteristic peaks down here. So this is the first thing you want to do, is make sure that your window is symmetrically located around the photo peak. Okay. Sometimes people do what they call an asymmetric peak. So in other words, they'll do this first, and then they'll acquire the flood, the uniformity flood, because that's your next thing. How many counts do you normally go for on your uniformity flood? 4 million? 5 million? 3 million?
500.
What determines how many counts you go for? What's that? Okay, Monica said a very important point. Intrinsic or extrinsic? Mr. Singh, what's the difference between intrinsic and extrinsic? Do you do floods every day?
No, actually they have me go to the clinic at 8, so they have the fluid should happen at 6 o'clock.
Okay, you need to get in there and you need to do the quality control on this. Okay, otherwise when the state comes to visit you, we'll be visiting you in jail. Right? When they do they do it with the flood on or off, or you've never seen it?
No.
You haven't seen it anywhere?
I guess it's a
We did that. In the first quarter, I saw some quality control over there, but it's my first time going there, so I'm not sure what they're doing. I think it's looking and stuff like that. So.
Okay. Well,
They have people at 8 o'clock, so.
I would strongly recommend that you get in there early, even though it's not your scheduled hours, because you're going to be having to do this on your own. What determines the number of counts is actually the field of view and the matrix size that you use. Okay, typically we want to get about 10,000 counts in each one of those pixels. So that means if you have a 64 by 64 matrix, you've got 40,000, or you've got 4,000 pixels. 10,000 counts in that means you need about 4 million counts. If you have a round detector head, then if you calculate the circumference of that and divide that into 4,096, it still works out to about 10,000 counts per pixel. Okay, that's your 1% error at 95% confidence interval. Okay? But intrinsic means that you do not have the collimator on. So you typically use a point source of technetium. Extrinsic means that the collimator is on, and you'll either use what they call a flood source or a flood phantom. Does anyone know the difference between a flood source and a, Mr. VF, what is the difference between a flood source and a flood phantom? Yeah, Monica. You gotta be faster in here, man. Monica.
The flood phantom is that hard shell that you inject the tech in there, it's filled with liquid.
Yes, okay. The flood phantom is like a giant aquarium. You inject an amount of technetium in there, you shake it up, make sure it's well mixed, and then you put it on top of your collimator. Okay? The problem with that is that it's messy. In my situation, I had a flood phantom. I had to squeeze the air bubbles out between my knees. That is why I am sterile to this day. Yes. Plus you spill it on the skin. Sympathy points. Okay. But the thing is that it is messy, and I mean, you had to get, it took time before you just were able to apply enough pressure to squeeze the air out and not all the technetium. Air bubbles in there will create artifacts, so you couldn't do that. The other one is a 57 cobalt source. The sheet. Yeah. So a flood source is the cobalt phantom. The flood phantom is the one that has the water filled that you mix technetium in. And the bad news, well, the reason why some people still use the technetium flood phantom is because it's cheaper. Okay, technetium is only about 17 cents a millicurie. You don't put that much in there. I think some people, I don't know, they put it in a range maybe 3 to 5 millicuries. But the cobalt source, on the other hand, is less messy. You know, it's real easy to transport, put on there. But the problem with it is, or what would be a problem with using that?
Once it gets old, it takes forever to do the flood and
Yeah, the longer you have it, the longer it takes. But I mean, you can probably use it for probably a couple of years, 3 years, 4 years. Typically, they get about 5 to 10 millicuries in there, and then as it decays down. But the thing that people don't like about it is that it's not the radionuclide that you're using to image patients with. So that's one of the big disadvantages with that. Plus, every 6 months you have to do a wipe test on it. I would bet that if I went there as a state inspector, I would probably find all sorts of little minor violations like that. Like, okay, what is the serial number of your cobalt sources? When was the last time you inventoried them? When was the last time you did a wipe test on them? Okay. The radioactivity does leach out through the plastic, so you've got to keep that in mind. Okay. So, like I said, you need to look at your spectrum. I think I showed you one of the problems that we had where one camera was peaked with cobalt and there was contamination on the detector. Did I show you that one? Actually, I think it's in here. Just to give you an idea about grainy images. Everyone recognize that? that a picture of there? It's carotid angiogram. Can you see how grainy the image is? Okay, that's because it's photographed off of a TV signal. And coming from a fluoroscopy unit, and there's very low photon radiation there. Well, I'm not going to, I'll find it, I'll show it to you after lunch. Okay? But going back to our story then, okay, so the next thing we do is we do a uniformity flood, and again, you should be able to determine whether you're doing an intrinsic or extrinsic. Okay, so how do you guys like that one? Okay, to go ahead and use the camera?
No.
Huh? You're saying something, Cynthia, but you're not saying it loud enough for... Okay, let's do a consensus. Mr. Singh, are you going to use this camera?
Say that again?
I say, are you going to use this camera? This is your flood.
No.
Why aren't you going to use that camera?
It has some kind of stats.
What's the problem with it? Describe it to me, please.
I'm not sure what's wrong with the camera, but
So you're going to go tell your doctor that you're not going to do any of his patients, and he's going to lose $10,000 a day because you're not going to image the patient, but you can't tell him what's wrong with it. Ashley. Gut feeling, yeah. Gut feelings, you can get your butt fired. Okay, so Ashley, what are you going to tell him? You going to say, yeah, let's get going, or let's not do it, or what are we going to do?
It's cut off on the left side.
Okay, so what does that mean? Use it or not?
No.
Don't
Not
use it.
necessarily.
Okay, the problem with this one here, and these people were using, now, I have to tell you, this is Martin Luther King Hospital. So it's stupid. I mean, they do dumbass things over there all the time. Okay, we have what they call an X and a Y gain. Remember those amplifiers we talked about that determine the location? Okay, you have to periodically adjust them to make sure that you're seeing the whole field of view. And this one here, the X gain is too amplified. That's why it's projecting the image off the end over here. All of the patients that you would image this camera on are going to have an elongated width. Okay, everything is going to appear wider. Okay? If we had this problem going in the Y direction, then everything would be taller and thinner. Okay? But this is the, I mean, people look at this, they get complacent, they go ahead and use the camera anyway. This thing should have been stopped that day that it first showed up. One of my students said, you know, Mr. Radke, I told him that there was a problem with it. A student told the techs, hey, you think we got a problem here? Okay, but that's the reason why, is because there's 3 amplifiers. You have one for the X signal, one for the Y signal, and one for the Z signal. If the Z signal was acting up, this thing would be like a little tiny dot. Okay? With the X and the Y, either this thing will be foreshortened or elongated like it is here. Okay? But you guys have to look at these. Okay? You don't want to, you know, do 3 months worth of patients and then find out every day you had something like this going on. Every one of those images should be repeated if that happens.
So on that one, which amplifier is acting up?
It's the X gain. Now, one of the other types of uniformity, okay, again, if you're doing intrinsic and extrinsic, there are some things that you have to be concerned with. Now, okay, so it says intrinsic, okay, utilizes a point source. Now, a point source has a very clear definition. Usually it's less than 0.5 cc's in a 3 cc syringe. Anything larger than that is no longer considered a point source. So we're trying to use what they call the inverse square law to make sure that there's a uniform distribution of radiation on your crystal so that it all looks the same. You don't want to see any hot spots or any cold spots. Okay? So the point source should be placed at a distance 5 times the diameter of the camera's useful field of view. Okay? Remember I told you there's what they call the useful field of view and the central field of view. Okay? Everyone remember the difference to that? Miss Cynthia, what's the difference between the central field of view and the useful field of view? And if you think I'm being hard on you, just imagine these questions being asked by the inspector from the state. They do ask you these questions. Mr. Radke, you think your central field of view is okay there? Well, I don't know. I'm only getting paid $75,000 a year to do patients. I don't have to worry about this other stuff.
Yep. That's the answer.
Don't count on it. You have a very short career. And I hate to say it, man, these people talk. So they'll go to the next hospital and say, God, you should, that place over at Radke's, man, they're going to close it down. As soon as I send this report in, that place is out of business. Now, if they see any really major problems, they'll shut you down. You'll get a cease and desist order right now. Okay? Over my daughter's place, these guys left germanium rods out, just sitting in the hall. You know what germanium rods are used for? 68 germanium. So if you were walking down the hallway and you saw them, you wouldn't be concerned. Oh, look at that. Somebody left their germanium rods out in the hall. Okay, that's what we use as the transmission source for PET scanners.
Yeah.
Yes, sir. Think it's a good idea to leave them out there in the hallway?
Just a little radiation.
That's a little radiation.
Yeah.
That's good for you, right? It causes mutations.
Yeah.
Mutations are good. Yeah. I could always use an extra eye in my forehead.
Just why go to the sun.
Yeah. Say, do you guys worry about sunburn? Because you'll get sunburned tonight because you can't see it, right? Never mind. Okay. Blonde joke. Okay, going back to our story over here. Okay. So, the central field, or the useful field of view, and all that kind of good stuff. Remember I told you that if you have a detector, you take a little bit of radiation and you put it over here, and then you start moving it. As soon as you see it on the persistence scope, put a little mark on your collimator, continue across, and then when you last see it go off and you no longer see it, okay, this is called your useful field of view. And you do it in the horizontal and the vertical dimension. So you understand that? Take a piece of get some radiation, like a little cobalt source, and then you just measure the distance where you can see it on your persistence scope. Okay? So that's your useful field of view. Central field of view is 80% of this. So if this measures 17 inches, and this measures, if it measures 17 inches across and 14 inches wide, then your central field of view, or your CFOV, is going to be 80% of that. So 14 inches times 0.8, and and 17 inches times 0.8, and that's your central field of view. The central field of view is where you do most of your imaging. Okay, you always want to get everything in the center of your detector. Okay. But here's the problem. Okay, especially with using a point source. Okay, first of all, you have to make sure that it's a point source. So I said here, less than half of a cc in a 3 cc syringe. A capillary tube, does everyone know what a capillary tube is? It's where they used to use it to draw blood. You stick yourself, and it's like a little tiny glass thing that sucks, don't use those, because that's not going to be a point source anymore. It says a capillary tube or TB should not be used. Why can't you use a TB syringe for a point source?
It's too narrow, so it can be too tall.
Yeah, and this is what you're trying to do here. Okay, here's your 3 cc syringe. And here's a half of a cc right here. Okay, in a TB syringe, this is half of a cc. Remember, these things are only 1 ml total dose. So the thing is, you want to keep a very, very small source of radiation so that when it diverges out from the point, you can actually use the inverse square law to make sure that you have an adequate uniformity on your detector. Okay, in other words, if you have this thing too close or too far away from the point source, then you might get an image that just has a big bright spot in the middle. And I'm going to show you that in just a second here. But so the key on this thing here is you have to make sure that that point source is 5 times the distance of your useful field of view. Okay. Are you going to see a question like that on my quiz? Absolutely. In real life, you do the same thing. Okay. The other thing I put down here, the source should be suspended in the air or appropriately shielded in order to reduce scatter radiation. Okay. In other words, how many of your people put this on the floor? They have the camera on top and they put the source of radiation on the floor. Okay, that's a big no-no. Because the radiation that hits the floor and bounces back up into your detector, especially on an intrinsic flood like that, is going to give you very poor uniformity. Okay? So you do not want to, the best thing to do is to take a little plastic bucket hanging by a string, and you can raise and lower the bucket, so when you put your point source in there, you can pull it back up, and it's 5 times the distance, and you don't have as much scatter radiation being detected by your detector.
What if it's in like a little lead thing?
Not good either. The lead is one of the worst scatterers of radiation. I mean, people, I'm not going to tell you that people don't do it, but I'm telling you, if you want to do it properly.
So why does it say or appropriately shielded?
It means something that's not going to produce a lot of scatter. Well, plastic. You put it in a plastic container, but the problem is anytime you have it on the floor, okay, it's better to suspend it in the air. If you can. If you can't, then that's what you got to do. But the thing is, you got to understand that it's not going to be optimal. Okay. Then the source strength should not be more than about 10,000 counts or a dead time of 10%. Normally, your cameras should have something on there that tells you what your percent dead time is. Okay. Remember that means that the thing is not able to process the information as quickly, so you're losing 10% of the information. You're getting that pulse pileup, and that pulse shaper can't keep up with it. And I don't know if you guys, most people just use technetium for their intrinsic floods. I don't know anybody that uses cobalt, but you can. And then the other problem you run into is the edge packing. You all remember what edge packing is? Mr. Villa, what is edge packing? Huh? Sounds familiar. Do you see any edge packing on this image? Yeah, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So you guys don't see any edge packing on that, huh?
Saturday we'll go little.
Huh?
By Thursday.
I'm glad they let us do that because, back in my day, we used to have to keep books where we had all that stuff in there and
Looks a little brighter on Saturday.
well, one of the things you guys gotta keep in mind is
So what's-
uniformity means that every day you do this, it has to be done the same way. Same number of counts, same intensity, nothing varied from the day before. So, just give me a second here. Let's see that. I don't know how these other images are in here. But edge packing.
Is that where the crystal is lined with the reflective material that makes it more rounded and heavy?
Well, what it is, you get like a black line around the outside. I don't know if you can kind of see it here on this one, I think.
Uneven.
What is it?
Uneven.
Well, normally it should be about the same looking completely around the crystal. What it is, if anyone can tell me what it is, you get to go to lunch today.
Go on Google.
Is it a brighter ring around it?
Yeah. But my question is, why does that happen? And I've got some really good pictures of it
High
here.
background counts.
Well, like, unlike an orbiter, I would sometimes see it, and isn't it when the photons kind of like bounce off the sides of the metal part and make it a little brighter around it?
Well, it's not bouncing off the metal part. Remember I told you that there's reflecting powder. Yeah. It bounces off the reflecting powder on the sides.
On the side of the crystal?
Yeah. And so you get this ring around the collar type of effect. So that's one of the things that you're looking at, you're looking for. And let's see. Now, if I do it, you don't see edge packing normally with this isn't a very good image of it here. But like I said, there's a dark ring that goes usually completely around. Okay? But the other thing is doing it with what we call extrinsic uniformity. And here's a good example of one here. A friend of mine asked me to go up and take a look at a hospital. So what do you think, Ashley? Are you going to use this or not?
No.
Why wouldn't you use it? Or what problems? Huh?
Has those dots on it.
Okay. We talk about this area here, right? What do you guys think that is?
Contaminate?
Cracking crystal.
Well, if it was contamination, it would be dark, right?
Two out?
Huh?
Two out?
Tube out's going to be a more larger round area than that.
Could it be hydration?
Huh?
Could it be hydration?
Remember, hydration causes measles. Those are going to be dark spots. Okay, so it's not that.
Is that where somebody bumped the crystal?
you're getting closer. Somebody damaged the collimator. Remember we said they used to have lead septa? And normally, to make sure that it is the collimator that's damaged, if you can, you rotate this thing 90 degrees. And if this thing moves when you rotate it, then that means that it's the collimator. Okay, does that make sense?
You can't rotate it, you can just do an adjournment, because it's done.
Yeah. Well, I mean, if I rotate the collimator, and it's, this I don't know why they did 3 of the same picture here, but normally, whenever I see something like this, I try to rotate the collimator, and if this thing moves when I rotate the collimator, then it's definitely in the collimator. Okay? If it stays in the same spot, that means that there's something wrong with the crystal, probably. Okay? Or with the computer. But so, intrinsic floods and edge packing. Okay, get extrinsic uniformity, and remember, if you just call it a flood phantom, you're probably calling it the wrong thing if you're talking about cobalt, because the cobalt is called a flood source. The flood phantom is the technetium one there, and as I said, if you didn't do it with extrinsic uniformity, you would have probably never caught that collimator defect. I caught it because I normally do intrinsic and extrinsic uniformity when I check a camera. You know, if a friend of mine says, "Hey John, you know, could you come over to my place to make sure that we're in compliance?" So I'll take a picture with all of their collimators, you know, their medium, their low energy collimators, just to make sure that a problem like that hasn't happened. And in this case here, as it turned out, somebody dropped something on it. You know, one of the janitors put his beer can on it. Yeah, probably. So the thing is that things like that happen, and that's not good. And I put down here the cobalt is used more frequently because you don't get air bubbles in it. It's not as messy. You don't have to put it between your knees to squeeze the air out. You get a high radiation dose. But I also put down here too that cobalt sources. Can anybody tell me what trace high energy contaminants it may have in it? The cobalt sources? When they make a cobalt source up, they don't ship it to you immediately. They let it sit for a month. Then they ship it to you. So my question is, what would be the other contaminant that you'd have to be concerned of?
Isotopes of cobalt, cobalt 58.
Okay, that's exactly the problem that we have, is cobalt 58. What's the energy of cobalt 58, Mr. Andy?
I don't know. I don't remember.
Ooh! Miss Monica, what's cobalt 58?
810 kV.
810 kV. And what's the half-life? 71 days. What's the half-life of cobalt 57? 270. So by letting it sit for a month, I allow the cobalt 58 to decay to a reasonable point. So when I send it to you, you're not going to be having problems with 810 keV photons going through your gamma channel.
Positrons it gives off.
That's not a big deal. Either way, either the 511 or the 810 keV, they're both a problem. So, and what percentage of the cobalt 58 decay is positron emission?
2%.
Is that a big deal? Okay. Now, this is done on a daily basis, or it better be, because as Andy, did you guys up to compliance? Was there any problems they found?
Yeah, no issues.
Okay.
More or less.
Because none that they told you?
Well, the state people walked away smiling, so it was sort of.
They didn't take the chief tech out in the backyard and hear this, "Trinity, aim!" We have an opening for a new chief tech.
Yeah.
No. anyway, so what you're basically looking for are hot spots and cold spots on your floods. And I gave you guys a good example with our while I'm locating it, I want you to take a look at this one. Do you guys have a GE dual head? Why isn't this thing showing up here? Is that upside down to you guys? Flip it. Yeah. Okay. Daily flood, that's the name of the patient. What in the heck is going on here?
Uniformity.
Uniformity. Okay, good, bad. What are you guys going to do with this one? I don't know if you've seen these gamma cameras.
It looks like it was done with the Phantom, and it was probably dipping in the center of the hot pot.
Well,
Isn't that uniformity correction?
yeah. What happens is that they've manufactured some gamma cameras where the heads only go like this far apart, and it rotates around like it has this cage. So you can only you can bring in the detectors, but you can only move them out so far. Okay, the source goes in between the two detectors, and so it creates this problem here. This is called a barreling distortion. This is what happens when your point source isn't 5 times the diameter away from the detector head. Does that make sense now? So if you were doing an intrinsic flood and you had your source less than 5 times the diameter of your useful field of view, it looks like a ball in the center. If you put any type of an object in there, you have what they call a barrel distortion. It looks like the ends are turning in on itself. So because of that problem, because you can't open up these 2 detectors further than that, the computer tries to artificially interpolate the data on the outside here. And I don't know about you, but that, to me, does that look good to you?
No.
No.
I mean, from what I'm looking at here, I've got a big hot spot in the center. Okay, and it looks kind of crappy going out towards the periphery. But that's the only way that this uniformity can be done.
Would it help if they use less filters?
Well, what would probably be better is if they, see now what they normally do is they have the two detectors are vertical to each other and they put a source in the middle. And then they rely on the software to do uniformity correction for them. My solution to this problem would be to take the cobalt source and put it on each head, individually. I would turn one head so that it's not facing the other one, and I would just do one head at a time. It's going to take twice as long, but I don't feel comfortable with this. And you guys probably can't see it as well with that big dark spot in the center. See if I, you can see it here. You see it's really dark here and then very light on the edges. So. But I mean, that's just the nature of the beast, so to speak. Well, it's lunchtime, so I think we'll quit with